high school engineering design and development class. And I'm Tosuf.
I'm Brad. And I'm Adi.
And our project was the Pyroelectric Presentation. We simulated that we work for a company, Quicksilver Incorporated, which is a large multinational company specializing in home appliances and various electronics. As part of the research and development team, we were approached by the CEO and given the task to work on a project which which would make their appliances more efficient and which could be used on current appliances or used in future appliances. So the appliance we chose to concentrate on was the refrigerator. Since it loses a lot of heat, which is basically energy, it's not exactly extremely efficient. And what we chose to use were pyroelectric material, which converts heat directly to electricity, assuming there's a change in temperature. And the electrical energy created will be stored in batteries to be used to power internal lights and various other displays. So I'm the team management lead, and Brian is the deputy manager, and Ade is the chief documentation officer and the security officer. And now I'm going to hand it over to Ade, and he's going to explain the original problem statement that we received and justification for the problem, and also background information on pyroelectrics.
So after we did some research, we came up with a problem statement. According to a survey made by the United States Department of Energy in 2009, about 57.5% of energy produced in the U.S. is wasted, mostly as heat. And this could be caused by inefficient machinery that produce heat energy, heat products as waste. Heat energy as waste. And this is just the problem. And we researched that in most home refrigerators is the second largest use of energy, of electricity, with 13.7%. And we researched that fridges use about 1,400 kilowatts a year, while a modern energy efficient model use about 350 kilowatts, which is about 75% reduction. And we found that the Department of Energy, the CEO estimate that we use about 100 watts of energy, or primary energy per year. And in exchange of a pre-1986 fridge for a new efficient saves the person about $158 straight. And pyroelectrics. And pyroelectricity is the ability to use certain material to produce temperature voltage and temperature voltage when they are heated or cooled. And we found out that pyroelectricity was first used in imperative detection. And this is the pyroelectricity. And this is the ammeter. And this circuit shows that it shows a change in temperature, showing a current going through. And this also shows it's a change in temperature, showing that there's a current going through in the circuit. And we noticed that pyroelectric materials are mostly used in long wavelength IR direction in doctrine. And this is picture taken with the pyroelectric material, and this shows this like white area shows no I heat going through it, and like this dark area shows like no heat. And pyroelectric conversion neutralizes low grade waste heat to produce clean energy. And this is our pattern. We noticed that the pyroelectric materials has been known for about 24 centuries, but it hasn't really been used until like recent years. And these are some of the patterns we found. And now I'm going to turn it over to Tosika to explain the casing material we use for our project.
As I already mentioned before, we're using pyroelectric material to generate heat. These are some of the material we received courtesy to Megate Systems. The PZT that's written above, it refers to, it's basically an abbreviation of the name lead synchronate titanate. Now, I know it has lead in it, but since it's in a compound form, it's not really dangerous as just normal lead is. And also, as you can see, these things are very small. They're very light and easy to carry, very compact, and just easy to use. And pyroelectric material, with most of pyroelectric materials, they have to be set up in different ways for them to work properly. Some have to be set up in compression design fashion, and some flexural, some shear. The two specific material that we got, PZ23 and PZ27. With PZ23, these are some specifications of it. And with the PZ23, it has to be set up in the shear format. And with the PZ27, these are some specifications. It has to be set up in the compression format. And we chose to use PZ27 in our project because since we'll be putting it on the back of a refrigerator in close proximity to the cooling fence, it has to be compressed down as far as possible. We're going to be using as low space as possible. So there's going to be a lot of stress on it. And since there's a lot of heat, it might expand. It's going to expand. So the expansion will also create a compression factor since it's limited to a particular spot. And this is a graph that relates temperature and voltage created across the circuit when by PZ27. Now, as you can see, the sensitivity is in millivolts per inch per second. So that basically refers to the fact that there has to be a temperature change rather than just temperature for the material to cause a voltage. Now, we believe that since it's per inch, we're going to get about 2 to 2.5 volts because we plan on covering the entire back of the refrigerator with it, and that's at least a few hundred inches, if anything. And since it's on a refrigerator, the compression unit is going to be constantly turning on and off, and that's going to create a change. We believe it's going to be around 10 to 20 degrees Celsius, and that's about when it creates the highest voltage. So we think that should work out. And I'm going to hand it over to Brian now, and he's going to talk about the various solutions that we came up with and the circuits that we decided to go with.
All right, here is our initial solution. For this, we have the pyroelectric materials represented here by the stack and over here would be the back panel of the refrigerator condenser, which is first of the need. And over here would be the circuit board. Our initial design for harnessing the energy, since it's a fairly low voltage, we would want to build it up over time to make it usable. So we were going to go capacitive bank initially, but we had problems with it discharging too fast and not staying on. So we switched to this idea, a synchronous buck boost converter. Basically, it takes the energy from the pyroelectrics and boosts up the voltage from the 2.5 up to 12 volts, which we would need to charge a battery, which would then hold the energy and then be able to be used to light the lights up and power various indicators. The specific buck boost converter that we had for our second solution was the LTC 3115-1. Delivers up to 2 amps continuous output for a single cell lithium-ion battery. And basically, input goes here, and depending on resistors attached and various other things, it will deliver different output voltages. Here is the actual chip, and there's the block diagram for how the circuit works. The buck boost converter itself offers a 2.7 volt to 40 volt range for output and input. And also regulated output with the input shown above in that circuit, and can produce voltage above, below, or equal to the input voltage. This is our final solution, which is the LT1110 buck boost converter. This is a little bit better for our purposes in that it is simpler and produces a better workable voltage. Here's a picture of us testing the pyroelectric materials pictured here, connected to a multimeter, and then put into warmed distilled water to heat them up, and then when we take it out, it cools down. As you can see here, it actually does produce a workable voltage that can be used in feedback systems for the refrigerator. Here is the basic battery charger we have, with some AAA batteries in it. Since they're about 1.2 volts each, putting them in series gives us around 2.4, pretty close to what we needed. And here's the breadboard. It's currently missing the LT1110 chip, or LT1110-5 chip, because we wanted to keep it protected as long as possible since it's static sensitive, and that could short out the chip. But we will show you after the presentation that we have put it in along with the diode. I'm going to hand it over to Tosa for our conclusion and recommendations.
So our recommendation to Quicksilver Incorporated is that we know throughout testing that pyroelectric material can indeed